Hello everyone, welcome. Let me know if you can hear me and see me. Just use the chat for that. Okay, great. Thank you, James. Hi. Perfect. Thank you. How are you guys doing? Good. Just going to wait for a minute for the others to arrive and then we can start. Good. Thank you, Brian. All right. In the meantime, I'm a bit curious. Let me know. I'm going to share a poll and let me know if you are from a tech background or not. So I shared it now. Oh, okay. So we have maybe 3 people not from a tech background. Interesting. So mostly a yes. Okay. For the one who said no, if you don't mind, can you tell me where are you, what's your background? Biology, interesting. It's good to have interest in all that's tech in the tech field. And explainability helps different domains. So I think definitely it can help you out in biology as well. Perfect. Okay, I guess we can start. We're 19 already. Oh, engineering embedded systems. That's actually tech, isn't it? That's interesting. I hope this is a workshop for beginners. I mean, anyone can understand. So, but I just want to make sure that you guys can all put in your questions in the chat. If you have any questions during the workshop, put them in the chat and I'll check it regularly and answer your question. Renato from Law, interesting. Are you trying to convert to tech? All right, let's get started then. Interesting. Okay, so I'm gonna start now. So today's workshop is about explaining explanation method in machine learning. So the first thing I just wanted to briefly talk about myself. I'm Mesa Zwambi. I'm a CLA instructor. So as I'm a data science instructor at CodeLabs Academy and also a PhD candidate in deep learning at the University of Lille. So my topics tackle neuroarchitecture search, a bit of explainability, a bit of machine learning in healthcare, a lot of domains. And I'm also an instructor at CodeLabs Academy, so I love to share all of the knowledge that I have through teaching and being an instructor there. So today I wanted to talk about explainability. And to start with that, I just want to kind of give a definition about explainability. There's nothing formal or a formal definition of explainability, but we can actually talk about explainable artificial intelligence or XAI as a set of processes and methods that allows humans or users to comprehend and also trust the results and the outputs of machine learning models. So the keywords there is allowing humans to comprehend and also trust, because maybe a data scientist or a machine learning expert could more or less understand what a model is doing, but that's not like comprehensible or understandable by any human being or by maybe the human being that would be using that model. So for example, if I build a machine learning model for a health practitioner or biologist or a person in law, maybe that person wouldn't really understand why the model is given a certain prediction. So explainability is all about trying to make what seems complicated, this process, this model, this black box that we will see later, understandable by a human being. So why is it important? Why do we need it? Like as I said, it's very important for a person that is using a model and it's in his daily life maybe to try to understand why it is given certain prediction, to either trust it or maybe see if it can take some information from that and do something else maybe, etc. So machine learning models are more and more used in high stake applications, for example finance, healthcare, law, a lot of things. So if it's high stake, it has to be accurate. We really need to understand what's the prediction coming from, why my model is given that certain information. So first thing, high-stake applications. Also, user need to trust this model to validate if it's fair, if it's not biased to certain things. And with time, we also have more regulations, AI regulations, especially in Europe. So we have the right to explanation in AI regulations. Sorry. So if a person or an institution uses a model and it affects a person, that person has what we call a right to explanation. They can they can ask that institution, why did you puts me in this or this category, like depending on the model used or depending on the function, of course, but they have the right to explanation. Like if, for example, it's a finance, it's a bank and it's using a model to predict if a person will or will not get a loan, and that person will see themselves refuse that loan, they have the right to explanation. Like, okay, that bank can just tell them like, no, you can't have that loan because the model predicted that you won't be able to reimburse it. They have the right to explanation, the why. It's really important. And also something else, which is deep learning models also need debugging. Sometimes we get bad results and we don't really understand why. So we have to understand how the model is thinking, or how my deep learning model is coming up with a prediction, to either change some things in it and debug it until it gets right predictions. Okay, so my question is, can you trust a model with high accuracy? Let's say I have a model, I train it on a test set, and it gives me very good answers. So can you really trust that model, even though they give high accuracies? And I wanted to answer that question with some examples. Okay, let's see the first example. Let's say I have a task of classifying the animals. So two classes, very simple. I have pictures of a wolf and pictures of the husky. And I want to make a deep learning model, a CNN, try to classify these images for me. Just a simple task. So I created this model and it gave me really good accuracy. Let's say 99% of the time it gets it right. And it's like it has errors on few images only. So can we really trust this model, or can we say that my model is perfect, it's learning right, since it's giving me a high accuracy? That I normally should say that, but if I take a look or try to investigate on the errors that it made in few images and see how it was thinking and why it made that error. So I have, for example, this image. So this is my model. It misclassified a husky as a wolf. And so this is the image of the husky that it misclassified. And I'll try to understand why it did that mistake. So we'll talk about techniques later, but let's say I used this technique that shows me where my model focused when making that prediction. In here, I can say that the way it's focused is on the background where it saw some snow. So this is how my model makes prediction. Like now I figure out how it makes prediction by looking at the background, which is not really a good thing to do because I'm trying to classify the animal inside the picture, not use confounding or background images, the background of the animal to do the classification. So basically here, what I understand from my model is that when it sees snow, it assumes it's a wolf. But every time it doesn't see snow, it says that it's a husky. And this is why it made a misclassification on the husky. So my model is very good at classification, but snow classification, not really huskies and wolves. So my second example is actually like classifying masses in mammographs. So I have this input image. that shows an anomaly. So this is a mass. And I have two different models, and two have very high accuracies, like 96% of accuracies for my both of my models. And they both predicted right for this input image. They said that this image is cancerous, for example. Now let me see, how can I compare these two models? They performed the same, they predicted the same on my input image, but can I say that a model is better than the other? Like, how can I debug, or how can I see the way of the model thinks when it makes this classification? So I try to look the same way at where my model focuses when making a prediction. So the first model, here I see this greenish, reddish, yellow colors. So when it's around yellow and red, it means it focuses on that area. So I see that my first model doesn't really look at the mass. It's kind of looks around the mass, and my second model like really looks inside the mass and the border of that mass, etc. So here, what can I say? I can say maybe that my model does, even though it does achieve very good accuracy, but it doesn't look at the mass to make the prediction. It looks at the surrounding of the mass, which is basically mean maybe the breast density. And usually when we have data sets, we have breast density. When the breast density is high, it means that the person is younger, which means it's less likely to have cancer, breast cancer, etc. So maybe that's what my model did. It learned to distinguish between a young person and an older person, instead of learning how to um, define the mass and define what makes a mass a tumor or not. So this is why, for example, we can't trust model number one. And okay, moving on to, this is real world application. So this is really this really has happened, and I don't know if you heard about this, because it kind of makes some noise when they figured it out. So we have this application called Compass. It's a popular commercial algorithm used by judges and parole officers in the US. So they have this application and they use it for example, try to predict if a criminal will do will get what how do we call it? Will get a subsequent offense at some point or not. Like they try to predict a criminal recidivism. So this is the idea behind Compass. And based on a 2 years follow-up study, they discovered that this model, or this algorithm, was shown to be biased. It was biased towards a Black defendant. They were predicted to be high risk compared to white defendant by, I think, double or something. So they did statistical research based on the prediction that was made by this algorithm over 2 years, and they compared it to what actually really happened in reality after that, and they saw that Black defendants were misclassified twice as much as being high risk of recidivism compared to white defendant, where white defendant were classified as less likely or low risk, falsely classified as low risk, sorry, twice as much as Black defendants. So here it's actually a big problem, as you can see, because without having explainability, without really understanding what the model was doing in the inside of it, we can actually get high stake problems because of it. And we also have another example, which was also famous when it came out, which is the Amazon recruiting system. So Amazon has a lot of applications every year, like thousands and thousands of resumes for people trying to get in a tech position. And so they wanted to make these automated systems that reviews resumes. So their aim is to like kind of automatically search for top talents. So they use this data set of 10 years period of um, submitted resumes, etc. So their algorithm knows which of these resumes is better than the other. So they try to make like this task of picking the best resume. And the model falsely learned that um, the fact that like over this 10 period, mostly the tech field was made or like flooded by men, let's say. So Amazon's system thought itself that male candidates were preferable. So it penalized any resumes that contain the word women, female, things like that. So it penalized it, like it was biased. It learned for itself that being a male was preferable, but that was just a reflection how was the tech industry doing over the 10-year period prior to that. Okay, so now how do we solve this problem? How can we understand machine learning models? And here we have to understand one thing first, that we have two types of models. We have what we call black box models and also interpretable models. So the first thing we need to, like, we have to make this difference. We only need to understand black box models because interpretable models, they give their explanation by themselves. Like they're intrinsic, in an intrinsic way, they're interpretable. So our black box model are what we need to understand, but the interpretable models, they are understood by default by the way they are built. And let's see some example for that. So for example, decision trees. Decision trees are understandable by human beings because we can actually see how the information flows. For example, here we have this Titanic data set for people for predicting if people survived or not. And for example, this is just a decision tree. For example, you can see the class that person survived because it was female and it was either first and second class, etc. So this is a visual. This is pretty much the speaks for itself. So any human can understand this decision. We also have models which are linear models. Linear models usually give the importance of features depending on the weights that they have when building that linear model. So we build a linear model, and the linear model itself give us some weights for different features, and we see the effects of different features on the outcome. And we also have rules. So rules also speaks from the cell. They're pretty straightforward and humanly understandable. They are built like this. So if a certain condition and another certain condition, then we have this outcome. So we can really understand why the model did what it did. So this is pretty much classical machine learning, decision trees, linear models, rules, etc. But lately we also have deep learning models that are also interpretable. And I'm just gonna give you this example. So this is what a proto-PNet architecture from a research paper that was out recently. So this is a normal convolutional neural network, but what's the addition to it, what makes it interpretable is that it gives what we call prototypes, and we'll see in detail what it means later, but this, it kind of gives the explanation with itself. For example, we have this example. So we're trying to classify bird species. So we have this input image of a bird, and it was classified into whatever species that is. And we also have the explanation with it. So our model basically tells us that I classify this bird as this species because it has a red belly that looks like this red belly that I found in my training set. And it has yellow feathers on the wings, which looks like the yellow feathers on the wings that it has in this species that I found in my training set. And in the head of that bird looks like a head that I've seen before. So it actually learned patterns or things that we call a prototype in a certain class, and it tries to compare this with the input image that it has. So it basically thinks like a human being. So it says this looks like that, so I'm classifying it as this. So this is pretty straightforward, understandable way of explaining things just like human beings do. All right, now moving on to black box models. So black box models usually, not like I just gave you a counter example, but usually neural networks are black box because they have a lot of weights, they have complicated architectures, they represent a very, very complicated function. So we give them an input, they do some transformation, and we have our output. Neural networks usually are not human readable at all. Like we don't really understand that big complicated function that we have with the weights and everything. So neural networks usually are black box. We also have SVM, support vector machines, are also considered as black box because we don't really understand what's happening in that decision boundary. And we also have ensemble models. So ensemble models basically are models composed of multiple models. So for example, an ensemble classifier is composed of multiple classifiers. Even if the classifiers themselves are transparent, the way that we combine them in ensemble strategies kind of makes them the output not that interpretable. So these are generic or the most popular example of black box models. All right. So how do we explain these black box models? What are the techniques? What are the main things that we have to know about this? And let's see. Okay, so first thing, this is kind of an illustration of how things go with black box model. So we have our data. We send it to our black box model. It gives us a prediction and gives that prediction to a user. So we don't really understand what's happening there because I have a black box model, as I said. So trying to explain a black box model actually happens after what we call post hoc explanation, because here the model itself is not explainable. It's not how we call it. It has to be post hoc because the model is already built, it's already fitted, it's trained, it's working. So we have something. We have to add something later on. So here I'm adding what we call an explanation method function or function F. So this explanation method helps me to understand my black box models and why certain prediction or certain data was predicted that way, etc., and gives that back to the user. So explanations methods are twofold. We have actually model specific and also model agnostic explanations. So explanations that what we call model specific explanations, this little box here, my F method here that helps me do an explanation depends on the black box model itself. For example, if I have a CNN and I try to explain that CNN using certain techniques, that certain technique um, only works on that CNN, for example, because this is what we have model specific. The explanation I provide only works on a certain type of models or certain type of architectures or certain type of neural networks or anything. So this is what we call model specific. But we also have what we call model agnostic, meaning that this explanation can work with almost anything. I wouldn't say anything because it depends, but let's say with almost anything. So my explanation method isn't bound or isn't dependent on the black box model. So I don't build it for that specific black box model, but it already exists and I can just use it to explain this black box model or another type of black box model, etc. So these are the two main things. Model specific, which means that my explanation only works with a specific models, and model agnostic explanations that work with different black box models. Just gonna take a break here and see if you guys have any questions. Okay, what do we do when a model has interpreted the wrong features? What's the next step? Okay, so here, depending on the type of model you're using, if you see that your model is using the wrong features or is doing something that is not right, for example, the predicting the snow or something like that, maybe you can try to penalize your model while it's learning. Like you say, if you're using the snow to predict, then you'll have a penalty. It's like you're trying to penalize it maybe in a loss function, maybe in something else. It really depends on the task, on the model you're using, on a lot of things, but there are ways like to redirect your algorithm to learn the right things from your inputs. Usually it's you could play around the loss function. Maybe you can play around with your data set. So for example, if you give it training set that contains a lot of snow and you say they know now that contains snow and contain a lot of huskies, and you say like it, you kind of force it to learn the right way. You kind of force it to detect huskies that can be in snow, for example. Okay, you're welcome. Let's move on then. All right, so now we saw model specific versus model agnostic explanation. We also have another classification, which is global and local explanations. So global explanation, what do we mean by that? If I provide an explanation for my model, this explanation can entirely give or entirely explain what my model do in its entirety. For example, um, if I have this decision tree that is trying to explain let's say I have a deep learning model that says if I'm going out or not, depending on the outlook, on humidity, on the wind, etc. And using some technique, I explain my deep learning model with a decision tree, which is this one. So this whole decision tree basically is a proxy that tells me how is my model thinking. So here I give a global explanation of my deep learning model. So I explain it global. I don't just explain one prediction. I explain how it's thinking in its entirety. So this is global explanations. We also have local explanations, and these are just to predict one or multiple predictions that are close to each other. For example, here, if outlook equals sunny and humidity equals no more, then playtimeness equals yes. So here, I try to understand why I have this outcome. So why playtimeness equals yes, and I try to see or investigate a little deeper, and I see that the outlook equals to that, humidity equals to that, and the wind equals to that. So this I try to explain locally, depending on the feature of that certain prediction that I have. Okay, I'm gonna check if you guys have any more questions. All right. So to sum up what we saw, model agnostic versus model specific, global versus local explanations. Now we can move on to some explainability techniques. So they're gonna be either global or local. They're gonna be either agnostic or specific. I'm gonna give some example, maybe the most famous one or the most used techniques, but there are a lot of techniques out there. Explainability is an ongoing research, so you can find many explainability techniques, but I kind of hand picked some techniques that could be interesting for you and that kind of are maybe the idea are quite global or quite accessible without a lot of math, without a lot of technicalities. Okay. First method is what we call global surrogate models. So global surrogate models, as you can guess, is a global method. So it's a global explanation. So the idea behind it is having a black box, and this black box gives certain predictions depending on this data. So I want to understand what my black box model is doing. And to do that, I can creates another model, and this model has to be transparent, has to be interpretable. So this model tries to give the explanation of my black box model. And how do I do that? How do I create from my black box model another model that is interpretable? So first I have to pick what kind of interpretable model is going to be. Is it a decision tree? Is it a linear model? Is it a rule-based model, etc. So I have first thing to do is I have to pick what kind of transparent model am I going to use to explain my black box model. Once I've chose that, what am I going to do? I'm going to take all of my data and I'm going to query it with the black box. So every time I put in my data and I get the expected outcome, so at the end, I will have my data set and the prediction made with the black box. So it's like I'm kind of having a new data set on my own. So I have data and the prediction made by the black box. And then I can train my surrogate model, this transparent interpretable model that I chose at first, and train it to make the same predictions as the black box model. So here it's coming to trying to learn to make the same prediction as the black box model did. So here it's kind of trying to approximate how the black box model is thinking. And we're just going to try to measure how far the surrogate model is from the black box. Usually they can be the same, so maybe we'll have some errors. So surrogate model can't really duplicate the exact behavior of my black box model, but I'll have something quite close to it. This method unfortunately has some limits because it's really hard to assess if that surrogate model is faithful to the real model. And there's even like some study that shows that we can create two transparent models that give contradiction explanation to the same black box model, etc. So surrogate models are kind of useful, but we have to be careful with them. Okay, next. Next is local interpretable model agnostic explanations. So here we have all the things at the same time. So this method is local and model agnostic. What does this method do? So we found out, like what I talked about with surrogate models for global explanations, they all don't always do well, because if I use a black box model, especially deep learning, usually the information or the mechanism inside of it is quite complex, so we can't approximate all of it with a surrogate model. So what we try to do is approximate some of it. So here, if you can see in this image, this global view, it's quite complex. We have a complex decision boundary here. The function is not linear. It's something quite difficult to explain or to approximate with a simpler function, because the word simpler here usually refers to our transparent model, because they're usually simple for human to understand, simple in their mechanism, kind of. So instead of trying to capture all that complexity of my black box model or of what it's doing, we're trying to approximate just a subset of it. Just this, for example, I take only one or multiple decision, and I try to understand them locally. Like I create, for example, a simple linear model that makes me able to understand how the features are important for that classification and for the neighboring ones. So here we're trying to train an interpretable model, just like we did with the global surrogate function, but here it's a surrogate function that's local. So we try to train it only using a subset of our data and try to understand locally what's happening around one or several predictions. Do you have any questions so far? Okay. Don't hesitate to put your questions, and I'll check from time to time to see. Okay, so Jason is asking, can you apply explainability techniques to interpretable models? So by default, interpretable models are already explainable, so you can understand what they're doing. So there's no any added values to trying to explain something that's already explained. Like, it kind of explains itself. Okay, so assuming an interpretable model is doing a poor job, um, you can actually debug it without having to use explainable techniques, because you can actually see why it's doing a poor job, because it's using the wrong features, because it actually provides this information without having to add any layer of explainability. So yeah, you can see it by itself. Like, for example, you have this decision tree, you can see why it's doing something wrong, and you don't have to add any explanation to why it's doing wrong, because you can actually see it extrinsically. Okay, so what is the neighborhood explained in Lime slide? Okay, so the neighborhood here is what I was talking about by the local thing. Here we have one prediction or the neighborhood of that prediction. It means we're still in the same area. We're trying to predict something quite local. So this is why we talk about when we talk about neighborhood. So we're trying to explain around one prediction or around multiple prediction. So my decision space is pretty simple around one or multiple predictions in that neighborhood. So yeah. Stein Nilsson is saying, I saw this for a moment ago and joined right away. Do you send a replay afterwards? I didn't get the first part. Yes, we have a replay. And I encourage you to stay, because now we're just explaining different explanation methods. So if you didn't get the first part, that's okay. I'll just try to give reviews from time to time. But yes, we have a replay that we can have later, but you can still follow and ask your questions along the way if you want. Okay, Jason is asking if local is a subset of features. No, local is a subset of the data set, not the features. So data set contains multiple data points, and a data point is composed of multiple features. So not the subset of features, but a subset of the data set. We're trying to explain subset of the data. Okay, perfect. Okay, let's move on to our next method. So this one is called partial dependence plot. So the partial dependence plot is a visualization method that can help us show how the prediction changes based on the input variable. So let's say I have a model that predicts for me the price of a house. And I have different features. For example, the building area, so how big is the house is, the distance from the metro or any transportation means, uh, and a lot of other features. So partial dependence plot try to visualize how my prediction changes. If, for example, here I'm trying to predict the price of the house, so how the price of the house changes based on the changing that happens in one or two maybe um, different variables or different features. So for example, if we take a look at the building area, we see how the building area like if the building area gets bigger, the price gets higher. Or for example, if the distance from the city center decreases, the gets higher, sorry, the price of the house decreases. So partial dependence plots are quite simple to calculate. We try to keep our data set with the same values for all the feature that it has and try to play around with the values of the feature that we're trying to explain or trying to visualize the impact of. And every time we try to look at how the prediction change over the time. So for example, if you play around with the building area and keep the rest of the features as they are, like we keep the values and we just change the building area and see how the price of the house is changing, and then we plot this partial dependence plot. Okay, next method, which is the SHAP method or the shapely additive explanations. So SHAP is heavily or just based on the game theory of optimal Shapley values. So there's this theory that helps us calculate. So in game theory, there's this a SHAP method that helps the Shapley value, sorry, help us calculate the contribution of each feature of or each player, if we're thinking about it as game theory, how each player um, affects the game or how each player contributes to a game. So here, for example, if we, for example, remove that player from our team, they the output is this. For example, they win or they lose or whatever, and then we can compute how the effect of removing that player affected the team, how the contribution of a player and another player. um, Shapley values, like, capture a lot of this, the contributions between different players, the contribution of a player alone, and things like that. So Shapley values can be used for explainability because they help us see not the contribution of players, but the contribution of certain features. So how a feature affects a certain outcome or certain prediction. How big is that effect? How that effect is when added with another feature, like the interaction between the features, the interaction of Shapley values help us see that and help us explain what each feature is doing, like my model, how my model uses each feature to make that prediction and how it impacts that prediction. So it is usually for local explanations. For example, I have my prediction, I have my feature, and I see every feature how it played around with that other feature to give me a certain prediction. But we can actually use it also for global interpretation or global explainability by just doing aggregations or plotting the different contribution of each prediction or each individual prediction. Like we try, like in this image here, we're plotting different contribution of different predictions of the using these features. So these are the shapely additive explanations. Let me check if there's questions. Okay, so Jason is asking, how can we be sure local explainability isn't biased since it only uses a subset of the data for explanation? Okay, it is biased actually. This is the idea behind it. It is biased because it only works on the subset that we train it on. It doesn't capture how the model is doing on any data point, but only on the data point it was trained on. So it gives explanation, but local explanation. It is biased locally, but it works on, for example, if I made a local prediction, like I explained locally, and that would only be useful on the locality that I use, like on the data point that I use for the explanation. It works for that certain data point, but it doesn't work on any data point because it's biased because it was built for only that data point. That's why it's local. Okay, so local explainability is useful only on for explaining those certain data points, and that's it. They can't use that explanation to help understand other prediction, but you can use it only to understand that certain prediction or the neighborhood of that certain prediction. Exactly. Yes. So we'll have to make it, if you want to understand another prediction, you build a local prediction around that prediction itself. So every time you try to explain another prediction, you just use that data point to make that local prediction. All right. So those were the Shapley additive values, or SHAP. We also have what we call example-based explanations, and these are very close to what humans do when they try to explain to you something. Sometimes when we have a problem and we give a solution for it, when we try to explain that solution to a person or to a user in front of us, we maybe give it an example. So we say, for example, like, this is actually what I'm doing during this workshop. I'm giving you examples for you to understand certain concepts. So something, some kind of explanation that was able to be implemented into explainability is given prototypes and criticisms. So prototypes are actually examples to make you understand why that certain prediction or what's the model thinking. Like I've shown you earlier, these images of a bird, we made this classification of a bird species, and the model itself told me that I made this classification of this bird species because it looks like this prototype for this prototype of another bird that I saw earlier. So here, using the prototypes, we can actually see how my model is viewing classes or the whole data set. So the prototypes is kind of a characteristic of a certain class. For example, in the prototypes image that I have here, I have multiple images of a zero, and this tells me how my model sees how a zero looks like. And these images of ones shows me like how's the prototypical or stereotypical image of a one is to my model. So it's kind of trying to give me the things that it learned from the data, because like my algorithm is kind of intelligent, quote unquote. It shows me how I give it images, I give it classes, and I tell it, okay, you have to learn what characterize each class. You have to do it. You have to figure out what makes a one one, what makes a three three, what makes a four four, etc. So these are handwritten digits, and my algorithm or my model is trying to understand or to classify handwritten digits into real numbers. So I gave my data set to my algorithm, and it learned on its own, and it showed me this, and it gives me this explanation. So, okay, after I trained on this data set of handwritten digits, this is how I see things. This is how I see zeros would look like, and this is how I figure out what ones would look like, and twos and threes and fours, etc. So these are the prototypes it gives me, and with using that, I can actually understand or see if my model is learning correctly, because as you can see in this image, it's doing things right. For example, if I gave this to my earlier example of that classifying wolves and huskies and the snow, etc., maybe if I give me a prototype of the wolf, maybe it will give me images of the snow. And this will show me that it's not really understanding what a wolf is, what a husky is, etc. So these are the prototypes. We also have what we call criticisms. So criticisms shows me what the model, even though they are close in shapes to the prototypes, shows me what it can't capture, what is not captured by the prototypes. So if I give it a zero that looks a little bit flat, and a five that's quite kind of scribbled like that, it wouldn't get it. But that's fine. Like, I understand the limits of my algorithm. I understand what it sees and what it can't classify as things using this criticism. So there are methods to actually extract prototypes and criticisms from your models. Okay, another example-based explanations is counterfactual explanation. And this is also something that's very human readable and something that we use maybe in our daily life. When we try to explain something, maybe instead of explaining that thing, we try to say, okay, but if this, like maybe I'm trying to predict if a student will pass a certain class or not, and I have their grades and everything, and I'm trying to explain to let's say they didn't pass that class, and I have the student, I have their grades and everything, and I'm talking to their parents, for example, and I'm trying to explain to them why they didn't pass that class, and I'm saying that if that person if your son or if your daughter had at least a 20 in math, they would be able to get to pass this class or something like that. If they had a 10, they will be able to a 10 out of 20 or something like that. They would be able to pass this class. So I'm not actually providing the explanation why they did fail that class, but I'm actually giving them a counterfactual explanation. So given like if this was if this has not occurred, this would have occurred. Like this is kind of a human readable way. We sometimes do that to explain something. We just give a counter example. So we try to implement this in models as well. So some models can give their explanation using counterfactual explanations. For example, here we have images of a 9, and we say to our algorithm, why is this a 9? And then it gives me a counterfactual explanation. So it wasn't closed on the top, it would have been a 4. So this is kind of an explanation for our model that it kind of gives me. But yeah, and a naive approach to generate counterfactual explanation is just basically changing things a bit randomly and see what makes the classification flips, so try to find the closest example that makes my classification falls into another category, and then explain this using that. So if this has not occurred, this would have occurred or something like that. So these are counterfactual explanation. Let me just check one more time if I have any questions. All right, no questions. Let's move on to the next one. Okay, so this is pixel attributions, and pixel attributions are model specific because they work on models that implements images or work with images, because we have pixels here. So they could be CNNs and maybe other models that can maybe even DNNs that uh, use or manipulate images. Okay, so pixel attribution, what does this explanation mean? So here we try to visualize or tell our models to show us where it was looking inside that picture when it made its classification. So here, if I'm classifying birds, I'm telling my model, show me where in this image is the bird, or where in this image, what was the element inside this image that helps you make that prediction. And as you can see here, the positive values here are in red, the negative values are in blue. So anything that is blue says that I didn't focus on that, or this didn't help me with my prediction, or this was something that contributed negatively to my prediction. And the red and positive values just show me exactly where inside of that image my model was looking at. And for example, if I did use this method on my algorithm earlier that classifies huskies and wolves, it will show that my algorithm focuses on the snow instead of focusing on the animal inside of the image. So there's a lot of pixel attribution techniques. We have occlusion or perturbation-based techniques. So methods like SHAP and LIME, so what we saw earlier, can also manipulate pixels, not just tabular data or things like that. So they can maybe turn off certain parts of an image to generate explanations. So what we saw earlier in that wolf image, if you remember, that snow, that's an occlusion method. So we kind of removed all the information that wasn't important and focused on the snow parts that was was focusing on, my algorithm was focusing on. And it's a local explanation. Why? Because it shows me like for that particular image, what my model was doing is was trying to approximate that prediction using only a subset of that part, just like focusing on that snow. We also have what these are the most popular, the gradient-based techniques. We have grad counts, we have saliency maps. These show, um, like I showed you in the previous slides, they use gradients. They use the gradients of a prediction. So when I pass my input into my model, it creates or it fires certain neurons and creates to create that prediction. And I can actually take a look at what weights were activated, what neurons were activated during that time to actually see what was my model focusing on. And using that, I can create um, my pixel attribution or my grid that shows me where the model was looking at. And we also have my path attribution methods. So path attribution methods, we basically have this base image and we have another image with a certain prediction, and we try to compare the two methods, the two images, sorry, and see where it was different, like kind of a counterfactual, not really counterfactual, but kind of using the reference to see what changed and what made this into this class and this as the base class of course. Okay, so let's see if you have any questions so we can move on to the coding parts. Okay, so Pavel is asking, how can we use explanation techniques in reinforcement learning? Same questions for RNN LSTM's architectures. Okay, so it is very useful to have these explanation techniques for these architectures, and depending on what this model is doing and the task that you're doing and the maybe the input or what you're trying to predict, you can actually use a lot of these explanation techniques. Either what we saw today, like the things that we saw, the different methods and techniques, you can implement them if they're model agnostic. For example, let's just think back let me just go back and show you this. Um, for example, if we take a look at this model agnostic method by creating a surrogate models that are interpretable, here basically you have your different models. They do their task. They have their task. You can actually approximate them using another transparent model. The only thing that you need to do is to query that different model, to query them, get the prediction, and use that prediction to train another model that is transparent to actually try to understand what your initial model was doing. But there's a lot of explainability techniques, and maybe you'll find specific or model specific explanations for RNN and LSTMs out there. So you have to just see what you have, see if there's any model specific algorithms that can help you with explaining your models or not, or maybe you can use any model agnostic method to explain your models. Great, thank you. Okay, see if I have any more questions. Okay, are prototypes and criticism generated by the model itself? Yes, yes. For example, the architecture that I shown you earlier, the proto-peanuts architecture, this architecture gives itself this prototype because it learns by creating prototypes that has its own mechanism that creates prototypes. So, wait, yes and no, because prototypes in my case here in the first example that I'll show you is actually an interpretable model by itself, but you can actually add layers to your methods to actually extract the prototypes and the criticisms for it. So if you add this layer after you have built your model, so if you have, let's say, a model that does this digits classification, etc., and you add this kind of layer that helps you extract the prototypes, the criticisms from your model, here you have an explanation that is post hoc. Post hoc means that happens after training your network. So your so the model is black box, and then you add this explanation to it afterwards. So you can extract. So the prototypes and criticisms kind of use elements from your architecture to extract these prototypes and criticisms. So, but you can actually build neural networks that gives their own prototypes from the beginning. Like you don't have to add anything to it. This is what they do. They give their own prototypes. They learn using prototypes in their thinking, and they give you that. And this is what we have with ProtoPNet actually. So it depends. Actually, sometimes they generate themselves. Sometimes you have to add some code to it to get or to extract these prototypes from them. Welcome. Okay, so let's see. Aroused at the coding part. And here I encourage you guys to open any notebook that you have, or a collab or something, so we can code along together and try to implement some of the techniques that we saw earlier. So we're trying to implement one of the most famous, which is the SHAP and also GradCam. So these two are very important techniques, and we're going to see them together. So let's do that. So I'm going to collab and I'm going to create a notebook, new notebook. That's it. I'll let you guys do the same if you want to code along. And let's going to start with the SHAP method. So I'm gonna name this SHAP code. So here what I want to do is I want to create a black box model. And this black box model will try to predict or try to um, predict the value of having diabetes or not. So I'm going to use a diabetes data set that I have inside of package. Is preloaded, so you guys can do the same. So the first thing I'm going to do is I'm going to install SHAP package, which will help me make this prediction. So pip install SHAP. So here, just to have things ready, this is the package that I'll be using for explainability. Let me see. Okay, so now it's installing, and now I'm going to create my model, to try to start create my model. All right. So I'm going to create my black box model using TensorFlow. So I'm going to import TensorFlow STF. And I'm going to import SHAP, of course, because this is what I'm going to be using. I'm going to import, this gonna makes that much space. I'm going to import sklearn dot model selection because I'll be using that to split my data into a training set and into a test set. You will see later. So I'm going to import, so I'm going from sklearn.model selection. I'm going to import the train test split. And let's see what else I'll be needing. I'll maybe use NumPy. So I'm going to import NumPy as NV, and I'll probably also use for visualization. I'm going to import from matplotlib plots as PLT. All right. So for those who open the notebook and code with me, letting you this to copy or try to follow along. All right, so first thing, let's load our data. So X is my data, and this is the prediction it has. So these contains the different features, and this contains the expected outcome. So I already have from SHAP, they provide some dummy or toy data set that you can play around with. So I'm doing just going from SHAP.datasets. I'm going to import diabetes. So let me just show you all the data set it provides with them. So we have diabetes, adult posts on here for predicting the prices of houses, California. They have a lot of the iris data set. They have a lot of famous data set there if you want to play around with those. But we're going to use the diabetes data set to do our prediction. Okay, so here I loaded my features, my prediction, the predictions, etc. Now I'm going to split them into a training set and to a test set. So X train, X test, Y train, Y tests, and I'm going to use the train split method here to do that. Train test splits. And I'm going to have my test size as 20%. So I'm going to leave out 20% for testing, and the 80% of the rest of the data I'm going to use for my model. Okay, and let's take a look at the different columns that I have. So I'm gonna do x.columns just to see what I have. So I'm making the prediction based on the age, the sex, the BMI, the BP, and these are different values that I have inside my training set, and they correspond to some metrics. I don't know much about the different metrics that impact diabetes, but these are just code names for them. So we're going to use these features to try to predict how much a person is advanced in diabetes or not. So there's numerical values that corresponds um, to that diabetes. All right. So now I'm going to create my model. So I'm going to create a neural network with this. So I'm going to import some layers to create my neural networks, and it's black box, and then I'm going to explain it. All right. Let's see. Just kind of let you guys follow along. All right. So here, the first thing I want to do is to create what we call a normalization layer. This is pretty much used to standardize the data or to normalize the data, because my data here, for example, age, BMI, and things like that, they have different scales. They're not centered. They're not between 0 and 1, for example. And why I'm normalizing them is basically because neural networks usually work better with data that is normalized. So we're normalizing the data to make them have the same scale, like they're all between zeros and one. And this is done by using the normalize layer. So I'm going to create a normalizer. And to do that, I'm going to get tf.cures.layers, and I have normalizer. Let's see. Okay, normalization. So here I created a normalizer. So what this does is basically subtract from the input the mean and divide it by the square root of the variance. So this is just normalizing the method. So it says that I have to first adapt it to my data set. So adapted means calculating the mean and the square root for this particular data. So that's what I'm gonna do now. So a normalizer, I'm going to take my normalizer here and dot adapt, and I'm going to adapt it to my training set to X train. All right. And now I'm going to create my model. And my model is tf.keras.models.sequential. So sequential because I'm going to create a normal multi-layer perceptron. So here I'm going to give it the list of layers. So the first layer is the normalizer layer. The second layer is a dense layer. So tf.keras.layers.dense. So here I'm going to create my second or my hidden layer, which will be a layer that contains 16 units. So, and has the activation function ReLU. And lastly, let's add another layer, which is my output layer, which is also a dense layer. And it will only have one unit because my output is just one numerical unit. All right, so that's my model. Now I have to compile it, and compiling it means telling it what kind of optimizer it will be using. So optimizer, I'm going to use the Adam optimizer, for example. Let's see if you guys have questions. All right, no questions. Okay, so I'm going to use the Adam optimizer and also use the loss function as mean absolute error, for example. Let's run that. Okay, let's see. I have an error somewhere. The layer added must be an answer class layer received. Let's see where the problem is. Let's say after keras dot layers dot dense. Yes, and then number of units, 1 unit. Okay. Let's see where the problem is. Strange. Let me just check where the problem is. We have sequential, we have a normalizer first, and then 2 dense layers. Looks good to me. Okay, let's see where the problem is. Just gonna copy this one then. And have this df.keras. Let's see if it's working. Oh yeah, tf.keras, sorry. We'll still send the same problem. Let's try to import keras then on its own and see if it's working. So from TensorFlow import keras. And I'm gonna run this again and see where the problem is because it doesn't seem to be working. Let's see. Let's add maybe, I don't think it's that, but let's try softmax. See if this is a problem or not. No. Then I don't know where the problem here is. Okay, so we don't waste that much time. I'm just gonna share to you the notebook that I prepared earlier instead. Some spelling error. What is it? Square bracket missing. Oh, okay, thank you. Thank you. Let me check again. But it's here, the square bracket. Here is this one is works with this one, and this one works with this one, and this one works with this one. So I don't see why it's not working. The ReLU, it seems to be working. Can you guys see where the error is? Issue with Keras layer, it runs. If you come on normalizer, it runs. Ah, so you think the problem is with the normalizer? The normalization layer, maybe. Let me just copy this one out and see again. Try again. Let's see. Okay, now it's working. I think, I don't know where I made the layers normalization. They seem to be working fine. I don't know where the problem was. I actually can't. Yes, I didn't adapt. Yeah, I shouldn't have done this. Yeah, that was the problem. Should have put normalizer.adapt and not set it to normalizer because this returns none. So this returns none. So it was thinking that this was none. Okay, now I see. All right. Okay, so let's now compile it and let's do the fit method then. So data receives model.fits. And here we're going to fit our model to train on our train set. So X train, Y train, sorry, and validation data is our X tests, Y tests, And also, let's put verbose to 0 because we're going to be using a lot of epochs here. Let's not have it's printing everything. So my number if epochs, I'm going to have around 200 or 400. Let's put 400 and see. What's the problem? Fit's got unexpected validation data, sorry. Okay, so now it's fitting, so now it's learning. And whilst it's doing that, let's try to prepare how to plot this. So here I'm going to plot the validation loss and the test loss to see if my model is actually learning. So to do that, I'm going to use pyplot, so plt.plot, and I'm going to plot from data.history, and I'm going to get my loss, and I'm going to label this as loss. And I'm going to also plot my validation loss to see if it's overfitting, if it's learning correctly, etc. So data.history, I'm going to validation loss, and I'm going to label it the same thing. Sorry, label loss. All right, and going to put on the legend here and see, and finally plt.show. Okay, let's take a look at this. Okay, so my model is learning correctly. So here we can see the loss decreasing for both training loss and also validation loss. So things looks good, but I still don't know what's happening inside because I have a neural network. So let's try to explain and see what's happening here. Okay, so here we're going to use our SHAP values and try to understand what's happening. Let me see. Thank you, Pavel, and thank you guys for trying to find the bug with me. That's really sweet. Thank you. Okay, now let's move on to the SHAP values. So now that I plotted my my model and I see that it's learning correctly, how do I know that it's actually using the right features to do its prediction? So here I'm going to use the SHAP values, the SHAP package to do that. And let's see. So the first thing we have to do is when calculating SHAP values, it's quite computationally expensive. So usually what we do is not we don't use all the training sets. So it's not actually kind of what we talked about earlier about local things. No, here we're going to summarize the training set into fewer points so we can calculate the SHAP values um, with the less computational overhead. So here we're going to call it X summary. So we're going to summarize, not pick a local site. No, we're just going to summarize our data set. And to do that, we can use sharp.k-means. So here it's an algorithm just to calculate or to summarize the data based on the k-mean samples of it. So I'm going to do that around my data X train, and I'm going to sample with 10 k-means. And then I'm going to use SHAP as from that. And then I'm going to use an explainer using SHAP.kernel explainer. So here we have a lot of explainers embedded in that. So we have GPU tree explainers, gradient explainers, color explainers. So these are different implementation to calculate or to create an explainer using SHAP. So we're just going to use the kernel explainer here. And this takes as input different parameters. So we have our model. So of course, we're trying to predict our model. So it takes model.predict. So it takes the prediction function of the model, not the model itself. And then, sorry, and then it takes just my data set as a summary, and then we'll calculate our SHAP values with that. Okay, so model that predicts, and it takes X summary. So we're trying using the data. If you remember that thing that we had, we're having an explainer, it uses the model, and it uses the data to create an explanation. So here we calculate what we call the SHAP values. So SHAP values are calculated using my explainer, and then it with just basically using explainer.SHAP values. So if you remember, I told you about that SHAP can make either um, local predictions, like local explanation explaining one instance, or maybe multiple global explanations by aggregating different local explanations. So here, I'm just going to try to explain the first prediction. I'm not going to explain all of my models, but I'm just going to try to see, to visualize the different features and how they interact into making the first prediction, and that's it. So here I'm going to try to, sorry, I'm going to try to understand how the test, the first, here I'm just selecting the first instance, sorry, selecting the first test to see what's happening or what's going on. And let's see, so here I'm calculating the SHAP values. So SHAP values show me how they, each feature contributes into a prediction. And now I'm going to plot it so I can actually visualize what's happening in my in my uh, in my method. So to do that with SHAP, you have to initialize shap.init.js. This is just for the visualization, because we're going to use what we call dot force plot. And this force plot function takes some parameters inside of it. First, the SHAP values. And actually, the SHAP values returns our matrix of multiple SHAP values. So selecting the first, getting the SHAP, it's a table of values. So we're just selecting the values themselves. And then it also takes in the um, the tests that we're trying to use, so the element itself, because with this we're getting the different column names and everything. So I'm going to put X test here. And also it gets something that is specific to SHAP values, what we call a base value. So if all my other features are null, or they all are at their base value, what kind of prediction that we will have. And this is we get that from our explainer by just basically typing in explainer that dot expected value. Let's see, expected value, and this is the first parameter. So here we're getting our base value. So if everything is null, everything is at its base, what will be the prediction? And then we're getting our SHAP values that was calculating using this method, this explainer. And then we're just using X test of 0 here just to get the names of the columns and the values of the features that we're trying to explain. And let's run that. Okay, I have a problem here. Let me select multiple. I think it's just looking for more than one, and just do that. So here I'm just selecting all the first one, just all the elements except until the first one. It's just instead of expecting one element, it's expecting multiple. Okay, let's see. What do we have here? Here I can see that my prediction was this value. So I don't really know what this means in terms of diabetes, but let's say I have this, this is my regression, this is a regression test, so I have this value that was predicted. What made this prediction happen? So here I have my base value. So if anything is null, I will have this value here. But since some feature interacted with each other, I'm getting this prediction instead. So this prediction, what does it mean? What made this prediction? What made the value move from the base value until this value? So we have different elements that contributed to that. So first, the S3 element made this contribution goes this way. For example, it made the contribution get lower. So the S3 was with this value there, made the value move from this to get in this way, but the S5 made it go higher. So this is like the impact of the different features. The S3 had a big impact in making the value shift this way, and this S5 made the value shift this way, and the age made the value shift this way, etc. So here we can see the different contributions that made our value get to this. So the different contribution that made this value get to this. So if you see this, what we can say is that S3 and S5 had big impact. Also, the BMI and the age, they also have very fair impact, let's say, but the biggest impact was made with this S3 here. And this is actually a visual way to see the different contributions of the features. Is it clear? Let me check if you have questions. Let's see. Okay, tell me if things are clear. Okay, great. So now that we've saw how to do this with one prediction, and it would be interesting to use SHAP as a global, kind of a global explanation explainer, but not really, like aggregating this multiple local explanations of each prediction into like visualizing what's like in the end, what was the most important feature. For example, in this prediction, the S3 was the most important one. Maybe another prediction, the BMI would be the most important one, and another, etc. So we're trying to see every time, or to calculate or to aggregate kind of a mean to see which overall which are the most important feature for my model or for my neural networks that I created. And to do that, we just use this SHAP values on more than one element. Let's say let's maybe take 50. Here I'm just taking subsets, not to make it local, but to just avoid computational too much computational time, but we can do that on all of the data set. Here, I'm just going to take a subset, for example, 10 or 15, just to see how it does. But usually you can take all of your data set to see what were the most important feature for your model overall. So let's calculate SHAP values and let's do a summary plot. So let's see. So here I'm going to do the same thing, but instead of calculating SHAP values for only one element, I'm going to calculate it for, let's say, 15 elements or 20. Let's do this for 20 elements. And then I'm going to use SHAP dot summary plot. Let's see. Okay, summary plot, and it takes the SHAP values, and it also takes this test thing that I'm trying, this bunch of information or bunch of values I'm trying to explain. Let's run this. It's going to take some time because it's calculating SHAP values for multiple elements at the same time, and then it's going to aggregate them into one visual or one illustration to see. Okay, so this is the explanation that I had for, so my data set only took 20 points, but you can take all of it if you want to, a global explanation of all of the data points. But as you can see here, the BMI was the one that's most influential overall in my data set. So in this individual one, we saw that it was the S3, but if you take multiple ones and aggregate them and everything, you can see that the BMI was the one that has the most impact, and then the S5 and the BP and the S3, etc. So this can kind of help you to see a global view of this explanation methods of what the model is doing. Sorry. Okay, let's see if you guys have more questions before we move on to another explainability method. Okay, if you have no questions, we're going to move to something even more visual. We're going to use what we call GradCam to see how my neural networks classifies an image. Then let's see. Just like the heat maps we saw earlier, we're going to try to do that now. Okay, let me create a new notebook and do that. If you want to follow along, go to your Colab or go to your Jupyter notebook or whatever method you're using to write the code with me. Let me do that now, Colab, and then I'm going to create a new notebook. In here, I'm going to call it GradCam because we're going to do some GradCam. GradCam. So this is a method, as we saw earlier, it's a gradient-based method for pixel attribution. And we're not going to create the model because here we're going to use the CNN. It's a convolutional neural networks for those who know. So convolutional neural networks are very, very useful with images and computer vision in general. So they're going to help us to classify certain images into a class. But there are already let's say, famous architectures pre-implemented in a lot of packages. So here we're going to use a architecture that is already trained, already out there. So We're not gonna create it on our own, but we're going to use it. So it's gonna be kind of fun. Let's see. So for using GradCam, like earlier I installed Shop, but for using GradCam, I'm going to use another package called TF Explainer. So let's take a look at it. So I'm gonna install it. Install TF Explainer. Let's run this. It's going to take some time to load. In the meantime, I'm going to um, get things that I need. Okay, let's see. TF, TF explain maybe. Yes, it's TF explain, sorry. All right, so now I'm going to, as I said, we'll be using a model that is already out there. So I'm going to use VGG16. So it's a model, a very famous model for computer vision for classifying images, sorry. And we're going to use that for classification. So okay, so I'm going to import TensorFlow as TF, and I'm going from TF.keras, sorry, .keras.applications, because it's already pre-built inside. So VGG16, I'm going to import, sorry, I kind of made an error here. Let's see, I'm going to import VGG, sorry, should be in, and I'm kind of sensing there's an error somewhere. Let's see. Okay, I knew there was an error somehow. TF. Yeah, let's just import keras from TensorFlow, import keras, and here I'm going to just use it directly like that. Still not recognizing it. Applications, I think I missed an S here. Yes, that was it. Okay, so here what I did is just basically took the architecture of Visual 16 as it is, and I'm going to import NumPy, so I'll maybe using it later. And I'm going to use this TF explainer, so I'm going to import, so sorry, from TF explain.core, I'm going to import GradCam, it's spelled like that. And I think that's basically it, maybe. We'll see if I'm missing anything, we'll add it later. So let me get my model, my VGG16 here. So I'm going to get it using VGG16. Let's name it model. It's better, model. Okay, so here, VGG16 actually give us a lot of things to play around with. So include top, it means that I'm adding the top elements, which is the 3 fully connected layers that is available there. So we're going to include the top here, but that's not what's most important in this case. Let me put this as true, even though it's the default. Yeah, it's the default. We're going to use this weights because we don't want just an architecture like that. We want it to be trained. So let's use the weights of the trained on ImageNet. What is ImageNet? So ImageNet is a very, very famous data set. It contains like billions of images, and they have like a lot of classes out there. So it's kind of one of the most known computer vision tasks. So the idea is to find the best architecture that can classify images in ImageNet. And I don't know, I think there's like 1,000 different labels inside of it. You can maybe check it out. Let me just check ImageNet classes. Um, let's see here. Yeah, there's kind of 1,000 class or something out there. As you can see here, there's a lot of classes inside because the data set is huge. There's a lot of it inside. I mean, I'll let you guys check that out later if you want. But anyways, so we want to take our models as it was trained on this ImageNet dataset because we want it to be doing something. We're not going to do that FIM methods as we did earlier. It's already trained. It's already knows how to do a job. So we're just going to see how it's doing that job. So I have my model here, and I'm going to upload an image to do the classification of it. So I know from this ImageNet thing, I have a class of cat inside, so I'm going to upload a cat image from my computer and just try to classify it with this model. So here I'm going to upload this file. You guys can do the same thing. Just try to find a tabby cat image on the internet. Okay, so I'm adding this image here. It's loading. And in the meantime, I'm going to wait a little bit for it to load. In the meantime, I can read this image using so image dot. I'm going to use keras dot preprocessing dot image dot. So this is just to read my image. It's now loading, so it won't. So there's this load image function inside that can help me load my image. So here I'm just going to give it the name of my image, which is tabby cat here. Tabby cat, and then I'm going to tell it the target size because my image may be big, maybe small. I'm just gonna give it the target size that is usable for VGG16. So this one is, I think, 224 by 224. Usually that's squared images like that. So target size is 224 by 224. 24, yeah. And then let me just make this image as an numpy array because I'll be needing np.array. Did I? Yeah, I did input numpy image. And let me guys show you the image that I picked for cat lovers. So plt dot, yeah, I didn't import matplotlib here. Import matplotlib dot pyplot. Come on. Okay, I'm gonna run this again. And I'm going to show you the image. Show image. Here, what's doing, it's loading the weights because it has to download those weights. And I have a problem here, which is no such file or directory. I forgot the extension. Dot. Yes, Pavel, thank you. Can you share the image through chat? I cannot, but you can just pick any image that you want. Like just go to Google and type in tabby image. Let me do that with you if you want. I'm just gonna show you how to do it. Just tabby cat image, just to images. And I picked just the first one, like I didn't just do something fancy. You can pick other cat images if you want, but that's a tabby cat. This cat with this cute stripes. Yeah, this is my notebook. So this is the image that I'll be using, and now I'm going to use my explainer to see how my VGG16 classifier classifies it. So let's create that. So where is it? So I'm going to create an explainer with gradcam. This is my explainer, and I'm just going to create a grid with the different pixel values that will contain my image. So explainer dot explain. So I'm trying to explain my image. And here, this explainer takes as input this validation data, and it has kind of a special way of showing things. So my validation data is actually a tuple. Here it is, you can see it here. It's a tuple that contains an ND array and also an optional ND array here. This optional ND array could be the class, but I won't be using it here. So I'm just going to take this. So it's a tuple. And first thing, it takes my image, and then it takes none because I'm not going to use that optional thing there. So this is my validation. And also here, just like the SHAP method, I'm going to have to give it my model. So it will use the model to make the prediction and try to explain it. So the model here, and also I have to give it the class index because it's going to classify it to a certain index. For the class index for tabby cat is Let me just see. I think it's 281, is it? Yes, it's 281. This is the class index of this tabby cat. If it's classified correctly, it will show me what pixels in the image it's used to classify it as this class. And um, let me import one more thing that I forgot, which is import CV. See if it's here. If I have to install it, yeah, it's here. Here just to change the colors a bit. So color map. So this is how the pixel will show what kind of color maps I'll be using. Um, color map. Why is it not working? Yes, color map. So CV2 dot color map. And I'm going to use this hot color map. So it shows the red means it's focusing on that area, and maybe lighter colors or colder colors would show something else. And finally, I'm going to plot this grid with imshow. Let's take a look at this. Let's see. Oh, here it is. So it's looking at the right direction. We can see here that my ImageNet is looking right at the face of the cat, and it's maybe taken into consideration the shape of the face, maybe the ear, a little bit of the ears, a little bit of the stripes that you can see maybe in the legs here. We can see that this one, this red one, is looking at the bright parts of the image. So let's say debugging this VGG16 on cats worked correctly. All right. Um, let's see if you guys have questions. I'm gonna let you type in this last part if you haven't finished yet. Yes, it's import CV2. Yes, Mary. Okay. Let me know if you finished typing this. All right. Okay. Let's go back to our slides then, if you finished. All right, so now we've tried some method. Let's talk about some open problems we have with explainability. Okay, so it does look like we're pretty advanced in explainability so far. We have a lot of methods. We have methods tailored to certain tasks, tailored to certain models, but we have some problems here. Like this is not done yet. The research in explainability still has some way to go. Some of the problems that we have for explainable AI is we can't really have a way to evaluate the goodness of an explanation. For example, we did provide some explanation, but can you really quantify if there are good explanations, if there are bad explanations? How good is it? How bad is it? There's this need of evaluating having this quantified value of goodness of certain explanation. And there's also a problem with formalizing the way what's an explanation is. In the beginning, I told you I'm giving you a definition of explainability, but it's still something not very formal. Maybe an explanation could be something like the reasoning. Maybe an explanation could be something just to communicate. There's a lot of ways to, or there's this problem. There's no formal way of explaining of explanation. Yes, there's also a way of how to quantify the grade of comprehensibility by a human being. And this is very important and this kind of social work to do because it has to do with psychology, how comprehensible the matter is using counterfactual examples more comprehensible for a person than using prototypes or criticisms or things like that. So there's also this kind of way that's not really tech related, but it's also an idea of that we do need for quantifying because we do need these measures to improve our methods to do something better for explainability, but it's kind of hard to tackle. And also we also have this last thing that's kind of very, very important with, is an explanation trustworthy? What if we have an explanation and this explanation isn't really what the model is thinking? How can we actually prove that the explanation we have is actually what the model is doing. For example, the global surrogate explanation that we saw earlier, even if I get a transparent model by curing my model multiple times and creating something transparent out of it, do we really know if this model represent that well? Even if they give like exactly the same accuracy and the same predictions, is it really what's the black box model is doing, or is it seeing something else that we can't really explain? So these are all open problems for explainability, but it doesn't stop us from using it. And I kind of put in this slide some resources for you. So there's a book about interpretability that's could be interesting for you. They give a lot of more of explainability methods out there, but that's if you like creating. I also gave you a survey about about different methods of explaining black box models, and there's also a curated list of machine learning resources for interpretability. But these are a lot of reading and things like that. Um, Easier way to do it is just like watching workshops or boot camps like these. So since you are here and you made it this far, I just wanted to share with you a bit about what is CLA, what we do, how do we make these workshops, how do we have other activities and stuff like that. So CLA, or Code Labs Academy, is a team of 22 people spread across 8 different countries, but our home base is in Berlin. We actually make boot camps in Berlin, in Germany. So we are an international edtech startup. We offer accessible boot camps related to technology for either students or professional wanting to, like earlier. That's why I kind of asked you to see if you have a background in tech, or are you in something else and want to convert and things like that. So this might be interesting for you. So this is something I wanted to share with you to see if you this might maybe help you with changing career or things like that. So we do offer a lot of financial plans, so money is not an issue. So depending on your budget and etc. So there's a lot of financial plans to just fit your budget. And if you work, if you have part-time job, if things like that, we also offer part-time, full-time options, maybe in person, maybe remote, hybrid, anything to fit your schedule. And also you can enroll without any prerequisites. There's just some work you have to do at the beginning to just level up to the same people in your class, but usually it doesn't require any like most it's always doesn't require any prerequisites, sorry. So yeah, these are some financing options for people in the UK. They can use Konoma, which is like you can pay in installments up to 36 month 36 times. We have go-kart lessons there. These are just financing options if you want. We also have discounts, just like for coming here today and attending this workshop, you have 10%, have 10% discount. And also, but there's not much time left for this one. We have a November special where you actually can get €1,000 off the bootcamp you want to choose. So we are in the 27th of November. So if you want to get this discount, it's time. um, so if you enroll to our boot camps or to our different tech boot camps that we don't just cover like I'll show you later on. We also have career services to like make you step up to the actual work venue. So we have resumes, cover letter interview sessions. You have one-on-one career sessions, uh, mock interviews, job and internship listings, etc. There's a lot of days of this. So this is for the upcoming bootcamp. So if you want to join the data science bootcamp, which actually provides machine learning, deep learning, we have a lot. Our curriculum is very, very rich. You can actually go out being an expert in these different fields. So, and we do like the thing is we cover a lot of novelty, so we don't just stick with the thing that are outdated. So in machine learning, for example, we have explainability, we have things about AutoML, stuff like that. So anyways, these are the upcoming boot camps if you're interested to join. They started, so all of them start in January, but you have options to do remote or hybrid or in person in Berlin. But if you still want to come to our workshops, you have a lot of things coming up. So these are the free workshops, of course. I highlighted the things that are related to maybe like machine learning, Python, and things like that. But we have like a wide range. For example, the upcoming one in 3 days is leveraging the power of LinkedIn. So here, if you want to make some networking and things like that, just the CLA Career Service offer this free workshop. But we have a lot of things out there. So this just the things that are coming up until December, but it's always updated. So just check the website if you want to catch up with the free workshops. Yeah, that's about it. So if you have any questions, let me know. I'm just gonna check the chat again and see. Um, Mary is asking, will we be getting the slides and the information about the bootcamp? Okay, so to get the information about the bootcamp, I'm going to send you the website so you can have everything inside of it, the workshops, the recording of the workshops, the contents and everything. You'll will also at some point, maybe they won't be ready now, but we'll upload the video and also exercises with them. So extra exercises to see if you guys understood the content well and everything. Thank you, Diana. Thank you so much. So I'm gonna send you something now. So I shared a an action button. You should find it and beside your chat. And here you can use it to give your feedback. And I'm just also going to create a quick featured action here to for you to visit the website for other workshops, for the boot camps and everything. Let me just do it real quick. Here, I put the link and I share this with you. So here, if you want to see the website. Uh, Thank you, Elena. Thank you for coming. Make sure to leave your feedback, all right? That would be very helpful. We'd love to have feedbacks from you. First time with machine learning. Oh, yes, this is really good. So make sure to join our bootcamp if you're new with machine learning. I'm sure you're going to benefit a lot of the courses that we provide. Just stay in touch. Either the bootcamp or the workshops. We have a lot to offer. Great. Thank you, Stein. I hope you enjoyed this. Thank you. Thank you, everyone. I'm gonna wait for you all to click on the website or the feedback form before ending the session, just to make sure everyone gets it. Yes, naive base is next. Make sure to get there. Thanks, Mary. I can see already 80% of you clicked on the website. That's very good. This one's a few minutes to see. Yes, the workshops are all updated regularly. We have a lot of content. And also make sure to check the bootcamp because they offer a lot. Yes, for now the workshops are online, but starting from January, you can have workshops in person. We may have workshops in person as well. It's without the discounts. So the prices are without the discounts. But if you register in November, or since you are in this workshop, you can get 10% off, or you can get the special November discount because it's the months of sales, as you know. Thank you, Michael. Thank you for coming, everyone. I really enjoyed teaching this one. All right. Do you have any more questions? Okay. So I think I'm gonna end this session now. I really hope I'll see you guys soon in other workshops or in the boot camp. All right. Goodbye, everyone. Thank you. Have a good day. Goodbye.